Let's introduce our next speaker. Adam Donenfeld is a lead mobile security researcher at Check Point. With vast experience in the mobile research field, from a young age, he has been hacking and reverse engineering for fun and profit. Prior to Check Point, Adam served in an Israeli elite intelligence unit as a security researcher. In his free time, Adam studies German. So let's give an applause and welcome Adam.
אוקיי, תרקוד ריקוד יפה.
באותו זמן אנחנו צריכים לתת למרצה שלנו לשתות.
אני נוגעת לך קצת?
זה בסדר, אני...
איך זה? טוב, שומעים אותך באנגלית?
Can you hear me?
Can you hear him?
Test.
Okay.
Thanks.
Then let him know that you can hear him. Thank you. Cheers. Woo.
Prost. Okay, so thank you very much for coming.
This is for you too.
Yeah. Today I'm going to present to you a research that we have conducted on OEMs code. So the agenda for today, first we'll talk about OEMs in general, how they affect our devices, their position in the Android ecosystem, and the differences between the various OEMs. Then we'll analyze two different zero-day vulnerabilities that we found in OEM code. And finally, we'll give out conclusions and see how we go through them from here. So just a little bit about myself. My name is Adam Donenfeld. I've been a security researcher for years, both in the mobile and in the PC field. I've mainly done security vulnerability assessment and exploitation. Currently, I work at Check Point as a security researcher for Android. In my free time, I also study German. Okay, so let's talk about our Android device. What do we actually get once we buy ourselves a new device? So first we have the Linux kernel with a few modifications like the binder, power management tweaks, wake locks. And then we have the Android project, abbreviated AOSP. The project is maintained by Google and can be viewed by anyone. It contains framework to expand the functionality of Android and contains essential user mode code for the operating system. Next, we have the chipset code, which brings both kernel drivers for the hardware, like for the GPU or for the camera, but also some user mode code for communication with the hardware. Next, we have the OEMs, which bring us unique customizations to the devices. The unique features come both in the form of hardware modifications, like the LG power button on the back of LG devices, or the edge screen on new Samsung Androids, but also in software modifications, like differences between the UI or different pre-built applications on the device. Now, it's important to mention that some devices do share the same feature with a different implementation. Finally, we have the carriers, which sometimes push a billing app to the ROM. Sometimes they print their logo on the device, but nothing special in matter of security. Okay, so the market share in the United States of the OEMs is fragmented unequally. There are a few large OEMs which share the marketplace among themselves. So it's enough to find a vulnerability in a major OEM to affect a very large portion of the market. Speaking of affect a large portion of the market and security, over the years, OEMs were known to have a low standard of security, and therefore their code was audited in the search of vulnerabilities. However, as the time passed, the problem received more and more awareness, and efforts were made to improve the security of the OEMs. These efforts came both from third-party contributors, the OEM themselves, and also from Google. So Google started to enforce new security mechanisms into Android, and that greatly increased the security standard of all the OEMs. An example for a security mechanism that I personally really liked, CTS, or Compatibility Testing Suite. Well, CTS is a unit testing framework for vulnerabilities. So once the vulnerability is published, a test is written to check whether the device is still vulnerable or not. And all the devices must pass this test. If a device doesn't pass it, it won't receive a certification from Google, and therefore it will lack many essential features like Google Play, Google Hangouts, and many other features. So Google is protecting us. Third-party developers contribute to the security of OEMs, and OEMs are getting better and better. Android is safe or not. So according to AndroidVulnerabilities.org, LG received the highest score for being a secure OEM. And we decided we want to test to check whether this score is justified or not. So we started a short bug hunting project in LG code. Okay, of course. Okay, so we want to attack a mobile device. There are two main attack vectors we have once we want to attack a mobile device: local attacks vector and the remote attacks vector. Local attacks vector means that I have an application installed on a device, an unprivileged application, and I can elevate my privileges to gain capabilities, which I'm not supposed to get using vulnerabilities. For instance, an innocent flashlight application or a tic-tac-toe game is not supposed to be able to read the call history of our devices. So it is for the local attacks vector. Remote attacks vector means that I have a unique identifier of your device. It can be your phone number, it can be IMEI, IMSI, it can even be an email address that is associated with the device. And using this unique identifier, I can coordinate my attack specifically against the device. Now, usually the user interaction in this kind of attacks is from minimal to nothing. So therefore, this kind of attacks are much more dangerous. However, with that said, usually remote attacks are not so common because they are more complicated. So let's start with local attacks. We start from the point that where we have an application, unprivileged application installed on a device. So there are many ideas that we can start working on, like privileged services that have no bind permission, native memory corruptions, even non-started services like Unix sockets that accept connections and can be attacked. So let's talk about bind permissions. Android allows applications to export functionality to other apps using services. However, obviously, an app will not want everyone to access its sometimes privileged capabilities. So the bind permission feature allows us to restrict the use of this exporting functionality. Now, this feature is used both by Android native apps, OEM internal services, and even by third-party applications. An example for use of this service, of this feature, let's say that you want to read the call history of the device. Now, the service that provides this information is protected by a bind permission. So only if we have this specific permission, we can access and read this data. So how does it actually work on a device? Let's take Facebook and Messenger, for example. Let's say that we are using Messenger and we log out from Messenger. So Messenger will attempt to log us out from the main Facebook app. So for this purpose, Facebook exports a service called cross-process logout service. So when we log out from Messenger, Messenger will use this service and log us out from the Facebook app. However, if we are a tic-tac-toe game, so we are probably unprivileged, and if we try to access this service from our unprivileged context, we will receive a permission denied exception. Okay, so that's everything you have to know to start our research. Okay, and excuse me. And how do we obtain this permission? In order to obtain this permission, we have to be signed by the same developer key, like Facebook's key. And since Messenger and Facebook do share the same key, Messenger is able to obtain this permission. So with this in mind, time to start the research. So we decided to go over all the LG applications that have some sort of exporting functionality, but have no bind permission protecting this functionality. Now, this is common because not every exported functionality is privileged, and therefore, not every exported functionality is supposed to be protected. So we found this service called LG ATCMD service. Now, this is a very high privileged service that exists on all the LG devices. Nobody should be able to access it. So if we are this cool guy here and we will try to access it, we're supposed to receive a permission denied exception. But we don't. Anyone, regardless its permission, origin, or developer key, can access this service use its high privileged capabilities and attack the system. So what can we do once we are connected to this service? We can start communicating with ATD or ATDemon. So what is ATDemon? ATDemon is user mode high privileged daemon that is written by Qualcomm and distributed to all Qualcomm-based devices. And now, unfortunately, there is no source code available for this daemon, so we had to reverse engineer it in order to understand how to communicate with it. Now, it's the main gateway communication to the firmware. We are talking mainly about the network, so Wi-Fi, GSM modem, Bluetooth, but also to Mini OS, which is an internal interface to test the device. Now, the most important thing about it, it receives commands from LG ATCMD service, which we are connected to thanks to the missing bind permission. So what can we do once we are using this service? We can read private identifiers like IMEI, Bluetooth address, etc., and it can help us coordinate our attacks. We can also overwrite these private identifiers, which are supposed to be read-only. We can reboot the device without any prompt or notification to the user, and therefore we can prevent the user from doing interesting stuff like removing us. We can switch between the different USB modes, so we can prevent a backup to the computer or a firmware upgrade from the computer. We can even go more offensive. We can wipe the device, again, without any prompt to the user. If it's not enough, we can also break the device. And my favorite, we can also lock the GSM modem, and this is also permanent and persistent after a wipe. And it's actually harmed the continuation of our research. We'll see soon why. So combining all these features together, we can create a very harmful type of viruses at a cost of 0 permissions. So don't download innocent tic-tac-toe games anymore. So again, so the exploit flow. We have a malicious application installed on an LG device, and we want to connect to LG ATCMD service. And since there's no bind permission protecting the service, we can just connect to it. And let's say that we want to issue commands like permanently lock the GSM modem, please. So we send this command to LG ATCMD service, which forward this command to ATD, which eventually just blocks the modem and harms security researchers. So we responsibly disclose this vulnerability. So if you have the newest version of LG, you are protected. Otherwise, any flashlight application can break your device. Okay, so we found a locally exploitable vulnerability. Let's aim higher now. Now, as I've said before, remote attacks are much more complicated, and the attack vector is relatively narrow. So how do we actually start? So we decided to go for all the LG applications which we can remotely communicate with, knowing just the phone number of the device. So I was speaking previously about the unique identifier. In this case, we took the phone number as our unique identifiers. Now, these applications can be identified because they must have at least one of these permissions here. Now, from all the permissions that we see here, WAP Push is the most interesting one because there is a lot of binary data that has to be processed on our victim. But before we talk about WAP Push, we have to understand first how text messages work. So all the text messages are based on a protocol called PDU. Now, PDU defines many properties in a text message, not just the text itself. For example, the sender, the receiver, is it ASCII, is it Unicode, the length of the text, and many other fields. Now, an advantage for us in this kind of communication, the mobile carrier doesn't run any verification checks on a device other than checking the sender and the existence of the destination number. Now, it means that lots of binary data will be processed on our victim. Here is an example of a PDU message. I'm not trying to teach you how PDU is tracked exactly. I'm trying to convey here that PDU is a complicated protocol. Nobody likes it, and therefore it was an interesting place to search for vulnerabilities. So now let's talk about WAP. WAP is the way to transfer binary data over the mobile wireless network. Whether you know it or not, you use it a lot. MMS are based on WAP. Carrier connectivity information, when we switch from Golan to Hot Mobile and you receive this update message, it's also based on WAP. The old vCards that were popular a decade ago are also based on WAP. And the old mobile websites, all mobile portals, that they are also based on WAP. And in order to access them, another WAP-based protocol called WAP Push was invented. So what can we actually do once we are with WAP Push? So we can transfer URLs to the device. We can transfer expiration dates for these URLs because these portals were meant to be expired. And since these messages were only meant to be sent by the mobile carrier, the protocol contains two important features, a delete feature and an update feature. So we can update any previous WAP push message that we sent before. So if you want to update the expiration date or the URL, and let's say that the message was expired prior to its expiration date, we can also delete it using the delete feature. So the way that WAP Push was implemented, most of the OEMs implemented it on the same way. It was some native library. But LG, on the other hand, they implemented it purely in Java in a package called WAP service.apk. And as the unique implementation, so was the unique vulnerability. So let's see the code that processes WAP service.apk and see how we got to this vulnerability. So this is a code from the manifest. We can see here that .push receiver processes this kind of messages, WAP push. And now let's see the code of push receiver. So the code the flow continues to sender validity check main. I'll summarize it for you. Eventually, we get to two different functions, process SI message and process SL message. Both are sub-implementations of the WAP push protocol, and they both contain the same vulnerability. So I'm going to give you like 15 seconds to see if you can find the vulnerability yourself. The vulnerability is both in the update and in the delete feature. Here's the update code, and here's the delete code. Take like 10, 15 seconds to see if you can find it. I believe in you.
It's circled in red.
It's a hint. OK, so as you can see from the comments that were placed there, we can completely control push handler.SIID. What? Who would believe? Yeah. So push handler.SIID is the unique identifier of the message. If we supply no unique identifier, then our URL becomes this identifier. And what happens if we send this URL to the device? So there is an SQL injection vulnerability that we can remotely exploit against any LG Android device. So we can delete or update any text message on any LG Android device, even non-WAP push messages, and regardless of the origin. So even if we didn't send this message before. So how do we exploit this vulnerability? In order to send a delete or an update message, the device must already have a pre-existing WAP push message. So we don't want to take any risk. We will first send a WAP push message to the device. So we sent one. Now we are sure that there is a WAP push message on a device, so we can send the delete or the update message with our SQL vulnerability. So we just send it, and arbitrary data will be either deleted or updated. Choose what we want. So again, we responsibly disclosed this vulnerability to LG, and they issued a fix for it. We received the CV number for it. Again, if you have the newest version of LG, you are protected. Otherwise, I can start deleting your text messages right now. So let's see a demo of this vulnerability. So the demo is the delete primitive. So let's begin. On the right, we can see the victim. We just have to know the phone number of the victim. And on the left, we see an attacker. The attacker is connected to a GSM modem, so he can send raw PDUs to the device. So as I said before, the victim must have a WAP push message in his inbox. So let's just send one. OK, so as you can see, the victim received a WAP push message. Now, it's important to mention that from this point, we can start exploiting the vulnerability immediately, but just out of curiosity, let's see the message. Let's see how it looks on the victim. Okay, so as I've said, this kind of messages were only meant to be sent by the mobile carrier, so there is no phone number on it. It's a service message. Now, a new update is available. Is a text that I chose. I could choose any text I wanted, but I think this one looks genuine, so that was my choice. Now, let's see how the message looks when you open it. Again, obviously, you won't receive a phone update from mitre.org. Again, the URL is completely controllable. Okay, now we know that there is a message on the device. Let's start deleting some messages. That's it. I mean, there is no. Thanks. Thank you. Okay, now let's talk about mitigation ways to protect ourselves from this vulnerability. So if we want to protect ourselves, we have to take out the SIM from the device, plug it into a non-LG Android device, receive the malicious text messages there, and then plug the SIM back. I don't think it's practical, but maybe people out there would use this way of protection. So this is for the delete feature. Now, there are a lot of malicious activities that we can do using this vulnerability. For example, we can delete a text message. Let's say that I hacked your bank account, and you receive this, your bank account password has been changed. I can just delete this message. I can even aim higher and delete all your inbox text messages and send you a new one. If you want your messages back, pay me. Otherwise, I will wipe your entire device. Maybe people will fall for it. I don't know. Haven't tried yet. Now, updating the inbox text messages is even more powerful. It is possible to craft very sophisticated phishing attacks. For instance, let's say that your bank account sends you a message to download their new version of app. Now, using this vulnerability, I can just modify the URL to point to my malicious website. It can point both to my malicious application or to my malicious fishy website. And hopefully, or hopefully not, you will put in there your credentials, and I will have them. Now, bankers like GMBOF, AceCard, and many others do that a lot locally. So doing this remotely is even much more powerful. Okay, so we found also a remotely exploitable vulnerability. Now, how much time do you think that this entire research took us? I want to hear your guesses. Okay, so I hope that you wouldn't be, but you're right. This entire research took us just 5 days. We are in 2016, and remote SQL injection vulnerabilities are still out there. Wow. Okay, so OEMs are still not good enough securing the devices, and unfortunately, we still can't trust them. Now, with that said, if you compare the situation to 5 years ago, we are in a much better world, and we're stepping into a more secure world. 5 years ago, it was very complicated it was really easy to find complete root vulnerabilities in OEM devices. So today, we still didn't find one, but we found also remotely exploitable vulnerabilities. So there is much to improve. But anyway, I hope that you enjoyed this research, and thank you very much. Now, if you have any questions, shoot.
Do we have any questions?
Yeah.
Do you have, what are the headers that are set? When you use the GSM modem,
GSM.
GSM modem on your laptop, and you connected it and you send a certain WAP. Do you receive on your phone some headers regarding the GSM modem that was used?
Okay, so the question was whether we receive, if we are the hacker and we send PDU commands using our modem, if there are other headers that the device processes, and the answer is yes. There are some of the processing goes on the Android code, so it's common on all the Android devices. And actually, there was a vulnerability that was found in 2014 by, I think it was Baidu, that allows you to open apps remotely. We found it, but I mean, it was already disclosed, and we thought that we found something, but too late. But it depends on the device, on the OEM, on the device. It depends on many things. But yeah, the flat answer is yes. Mm-hmm.
So like the vendor ID of the GCM modem as well and stuff like this, would you like whitelist the modems that you want to talk to your phone as a method of mitigation against like this kind of attacks?
So the question, correct me if I was wrong. The question was if you can mitigate this vulnerability if you sit on the, if you're located on the between the components that process these messages, right?
If you know what is like the GCM modem that is like the vendor or the MAC address, I don't know, it's supposed to talk with your phone and you can whitelist it.
So it depends. It depends where you're, how privileged you are, because if you're just a vendor, so I mean you can't. I mean in the chain of dependency, this component WAP service.apk will receive the messages before you. So you can't really mitigate it. You can receive this message by yourself, and then you can like prompt the user that he is being attacked, but there is no way to prevent it. If you are like an APK, you know, if you are a vendor, if you are like a security solution or something. Now, any other questions?
Yes.
Mm-hmm.
It's only for LG free and flow.
Excuse me?
The vulnerability
Mm-hmm.
for LG, only for LG?
Yeah, so the question was if it's only for LG. So yeah, we had both LG G2 and LG G4, and we successfully exploited it. But we recently got a G5 device, and I think that if you buy it and you don't upgrade your firmware, then you're still vulnerable, as far as I remember.
G3?
Also, yeah.
Yeah?
Mm-hmm. So be safe with your device. Okay, any other questions? Yeah?
So for the local expert, can you explain again how do you find the service that not be
Okay, so the question was how to find this kind of service. So since I work at Checkpoint, we have a very large database of applications, and we have advanced indexing tools. So it was very, I mean, I have a GUI and I can just mark a checkbox, unprotected services, but if you would want to do it on your own, you can just write a simple Python script that, I mean, every APK is a zip file, and you can just unpack the zip, and there is a file called androidmanifest.xml, and you can just find a second, and this file was, I mean, there is nothing you need to unpack, no encryption. You can just see this file after you unzip the APK. Just a second. Excuse me. It was in the remote demo. Sorry, but yeah, I mean, you can just see that Android time. I don't know the word in English. Sorry. Android permission. I mean, if it's missing, then anyone can access it, and if it's exported. So, I mean, it's pretty simple, and you don't need any advanced indexing to do that. I mean, but it is the life. Any other questions? Okay, thank you very much. I hope you enjoyed.